Our class. Today we're gonna start talk about mass transport in part 3. The mass transports are available in part 3 in Bird's book. So if you can see here, so this is a part 3 mass transport. We're gonna start talking about what is diffusivity and the mechanism of transport, and then we will explain much more about a concentration distribution in solid and laminar flow. Okay, let's start. Let's open your Bird book in part 3 in chapter in mass transport in Bird second edition. We're gonna start in page 513. Right, so this is diffusivity and the mechanism of transport. So in chapter 1 we began stating Newton's law of viscosity. In chapter 9 in heat transfer we began with the Fourier's laws of heat conduction, and in this chapter we're gonna start about explaining about Fick's law of diffusion. So imagine we have a water, and then there is potassium permanganate. We put a drop of potassium permanganate in water. Potassium permanganate has a color of dark purple, and first it's gonna start very dark purple and very concentrated solution of potassium permanganate, but over the time, because of there's some concentration gradients, the potassium permanganate will diffuse away from the crystal, and then later on, after some time, there's a diffusion, and then later on the water will change from clear into a little bit of purple region. So we're gonna call Fick's law for binary diffusion, and we're gonna define diffusivity DAB for the pair AB. Okay, so diffusivity would be included in all multi-components, start with 2 components, 3 components, 4 components, and multi-components. But what we're gonna talk here is all just for binary component, only for two components, which is A and B. Right. Before starting discussion, we will establish the following convention. For multi-component diffusion, we designate the spaces with lowercase Greek a, alpha, beta, gamma, and the concentration with corresponding subscript. For binary diffusion, we use capital italic letter A and B. Right. Let's open the next page and see. You can start seeing quite familiar graphic similar with the momentum transfer and also with the heat transfer. First we have a slab of fused silica, so it is a solid, so from there is a plate with the thickness of Y. It has a slab of fused silica. So silica is like a glass, so fused silica looks like a transparent glass. We call it fused silica is a substance B, and there's nothing in it, so the mass fraction omega 1 is 0 at T less than 0. At T equal to 0, at the outer plate of silica, we put let's say helium. The helium, we call it A, and the mass fraction of helium is the mass of helium divided by the mass helium plus silica, in the given macroscopic volume element. And this is so there is an omega 0, and because if there is a concentration gradient in here in the outer layer here into the with the inner layer, over time with small t there would be a diffusion, so the diffusion will start from the bottom to up there, where the helium will start to diffuse, go to red. So here gonna be the concentration profile of the helium. So when the large T, or when it is steady enough, we can see the the buildup of steady-state concentration profile for the diffusion of helium substance A through fused silica or substance B. The symbol WA stands for mass fraction of helium, and WA0 is the solubility helium of fused silica expressed in mass fraction. Right, so if we can see here, in steady state, we found that the mass flow of omega A to over the plate of the thickness of Y in helium in the positive direction, we can describe it with a good approximation of the concentration omega AY over the A is the area, would be equal to the rho, the density, multiply with diffusivity, multiply with the concentration gradient, which is the omega A minus 0. 0 is the concentration of A at the outer plate, the outer plate, this sides, and divide by the thickness of the fused silica. So the mass rate of helium per unit area of, we call it mass flux, is proportional to the mass fraction difference divided by the plate thickness. Here the density is the silica helium system, and the proportional factor, we call it DAB or diffusivity. So now we can rewrite the differential element within the slab in equation 17.1 strip 2, which is a J A. So this is the mass flux of J at the direction of Y would be equal to minus, which is the difference direction of rho dAB of the and its differential dWA minus dy. Here, omega Y A has been replaced by JA, and the molecular mass flux of helium in the positive Y direction. Note the first index A designates the chemical species in case helium, and the second index indicates the direction which diffusive transport is taking place. In this case is direction.